Human Society must actually and Arabic about the introduction. So polystyrene are the polymers with the composition of S and RPN that consist of polymer backbone covering bonded to thin atoms. Polystyrene are the only example of characterized polymers that are composed of a backbone of covalently bonded metal atoms. A remarkable feature of this class polymers is the delocalization of electrons along the polymer backbone. Sigma delocalization by electron might be also involved if the aromatic groups are bound to the thin atom of the dimension sigma pi delocalization. Synthesis of polystyrenes, we have a three types of method, which is the Wood type coupling, electrochemical reaction, and catalytic dehydrogenations. First, we have Wood type coupling. It involves sodium in organic solvents. It gives low yields and cyclic oligomeric byproducts. The yield linear polydipolystyrene of high monomers is obtained. Second, we have electrochemical reaction. Polystyrenes are prepared by electrochemical process that to be punched. The yield obtained are about 13 to 16%. The products often contain an unknown fraction of cyclic oligomers. So, for the third method is catalytic dehydrogenation of thin dihydrides. It is the most widely applied way to produce a polystyrene. Catalysts such as zirconium, rhodium, and platinum is used. So, we have 5 chemical and physical properties. First, we have an NMR spectroscopy, which is SN-NMR. The chemical shift of S and R to N can depend substitutionally on R. Premium polydioxide sternanes, including ferroterminated polystyrene with chemical shift, typically between negative 189 ppm and negative 195 ppm. However, if the R is negative, we show negative 170 ppm and corresponding cyclic oligomers around negative 200 ppm to negative 200 ppm. So for the hydrogen NMR, it is distinguished linear polystyrenes from cyclic oligomers. The distinction of the signals between cyclic oligomers and corresponding polystyrenes in hydrogen NMR spectra can depend on the solvent. Therefore, the NMR can apply for quantitative determination of the ratio of polymer and cyclic oligomers only in the cases where the signal of cyclic oligostyrenes and polystyrenes distinguished. So for the carbon NMR, the 13 carbon NMR spectroscopy has found so far relatively little indication in the characterization of polystyrene as it hardly provides additional information to the result obtained from the 180 NMR or 1 hydrogen NMR spectroscopy. Secondly, we have a solubility. Most polystyrenes reported are soluble. Example of polydioxide sternanes, including semi-terminated polydioxide sternanes, are soluble in several organic solvents such as benzene, toluene, tetrahydrofuran, or tetrahydrofuran. Polystyrenes will be substituted as a group dissolved in certain solvents such as tetrahydrofuran. So third, we have a density. The density of polydioxide sternanes tend to decrease with the increasing length of the RP group as the content of the heavy thin atom decreases. Care is not linear, as also other effects such as the packing of the molecules influence the density. So next, we have the electric conductivity. The conductivity of 3 times negative 8 SCM negative was found for polyester for spinel polystyrene around room temperature. Increase in temperature also increase the conductivity. And lastly, we have a UV spectroscopy. The yellow color is a characteristic for polystyrenes. As the polystyrenes are sensitive to the light, degradation of polystyrenes can proceed already during measurements in a UV spectrometer. The wavelength at the maximum absorption of polydioxide including polymers, with the ferroterminated RK group emerge typically in 370 to 400 nanometer. In aromatic polystyrenes, sigma and pi conjugation can be present which shift lambda maximum to the higher wavelength compared to the polydioxide. For polystyrenes, wavelength maximum show 470 to 480 nanometer was observed.
Assalamualaikum and good day to everyone. My name is Ainun Azurah and today I would like to present my part, which is the experimental part. This was based on article Kappa 2C and hypercoordinated oxazolene organotines, which is the monomer construct for stable polystyrenes. The main objective of this experiment is to synthesize the hypercoordinated tetraorganotene 4 compounds with the presence of oxazolene ligands. This is the final product that we want to produce, which is thin oxazolene polymers. In this experiment, we label it as polymer 15. These polystyrenes can bear more rigid group and it does not share the same level of flexibility. Next, we will discuss briefly about the synthesis of hypercoordinated tetraorganotene 4 compounds with oxazolene ligands. The synthetic methodology involved lithiation and transmetallation, halogenation, reduction, and polymerization. And in this experiment also, we use instruments like NMR spectroscopy, X-ray crystallography, mass spectroscopy, gel permeation chromatography, GPC, and DFT. Next slide is the steps used to form thin oxazolene polymers. The first step is the reaction of lithiated oxazolene precursor with 3-phenyl-tin chloride, and it produces a hypercoordinated stannum 4 oxazolene complex, and we label it as compound 4. The second step is halogenation, where the oxazolene sternanes undergoes bromination to produce the halide derivative of a compound 11. The third step is the reduction process using sodium borohydride to produce dihydride species, which is thin dihydrides, and forming a monomer 13. Last step is the preparation of thin oxazolene polymers. The dihydride derivative undergo dehydropolymerization to form polystyrene. The polymer display low molecular weight and stability challenge, which indicates room for optimization. The experimental also happened in controlled conditions, including low temperature like 0 degrees Celsius and inert atmosphere. This is essential to ensure to the stability of the product. In the last slide, we can see the result of NMR spectra of the final product, which is polymer 15. From the picture, it shows the 119 stannum NMR spectroscopy, where a single resonance at negative 183.8 ppm present, and this indicates the thin environment in the polymer structure. The part A above shows the crude spectrum of polymer 15. Meanwhile, the result of B below shows the clean one of spectrum 15. The result also shows the consistent with the coordination in the polymer chain. I think that's all from me for the experimental part. Thank you for listening.
Hi, my name is Nurul Ain. I will present to you about main finding of these articles. Polystanes as advanced material for optoelectronic device can be included in 4 types, which is optoelectronic properties, conductivity enhancements, stability challenges, and lastly, hypercoordinate structures. So first, for optoelectronic properties, the localization of SN5's electron into sigma-sigma bonding orbitals along the polymer backbone, such as lower band gaps and enhanced metallic behavior compared to other group 14 polymers. Second, conductivity enhancements. When doped with strong Lewis acid like SBF5, the conductivity can be increased dramatically, making them viable for use in electronic properties. For example, organic light emitting diodes, OLEDs, and organic photovoltaics, OPVs. Third, stability challenges. Attribute to increased steric hindrance and electronic saturation provided by additional coordination sites which hinder nucleophilic attack and degradation. And lastly, hypercoordinate structures. Hypercoordinated thin centers through functional ligand has been shown to improve stability. It can enhance the electronic properties and reduce the likelihood of degradation, making the material more viable for optoelectronic applications. Next, applications in the field of electronics can be seen first in conductive polymers, enhanced through dropping, makes them suitable for applications in organic electronics such as OLEDs and photovoltaics. Second, flexible electronic can be processed into flexible films, making them ideal for use in inflexible electronic devices, allow for the development of lightweight and bendable electronic components. Third, charge transport layers, examples are LEDs and solar cells. Ability to facilitate the movement of charge carriers, electrons and holes is crucial for the efficiency of these devices. And lastly, for sensors, due to electronic properties and ability to modify their surface chemistry, so it can be respond to specific stimuli.
We have 3 main points, which is synthesis and characterization, surface interaction, and stability of polystyrene. First, we have synthesis and characterization. Synthesis of a series of organic compounds containing oxide facilities. Compounds characterized using NMR spectroscopy and X-ray crystallography. So second, we have surface interaction. We first degenerate around the atom into a disordered 3.5 arrangement. Presence of a short SN bond then in a synthesis compound indicates non-coordination. So last, we have stability of polystyrene. The incorporation of oxide compounds was found to enhance the stability of polystyrene.